Let me go for another 15-20 minutes, then I'll stop for today and give you one more important concept. So we looked at the concept of PCA, and like I said, PCA is the main goal is dimensionality reduction, right? For example, 784 to 200 dimensions and so on. Okay, so what exactly is it doing? So even if we apply a PCA, right? So here's our 784 by 1 data. So here's our 200 by 1 data, right? And if we feed it to a neural network, and let's say so this is acting as a classifier. Okay, so if we have 10 outputs, right? Earlier I mentioned if we don't use the PCA and if we simply have 1,000 training data, our maximum accuracy you'll get will be around 90%, right? If we use the PCA approach, it gets better. So the question is, just simply reducing the dimensions make it better, or is there something more to it, right? So in fact, there's something more to it. What PCA does is, of course, I cannot draw 200 dimensions or 784 dimensions, but basically PCA does a couple of things. Let's say let's pick the 2-dimensional data. Instead of 784 dimensional data, let's just take a look at 2-dimensional data, what's going on. Okay, so let's pretend here are some of the data points. Okay, so what does the PCA do first? If you recall, we computed the mean of the data, and so what will that do?
Center everything.
That will center everything, right? So this will center something like this. Okay, so then what it does is it computes the basis vectors. Okay, so the way it computes the basis vectors is, and that's important, when we sort based on the highest eigenvalue or highest eigenvector, it's a vector is basically, so for example, if this is in 3 dimensions, if this is 1, 0, 0, right? A vector is basically, if we draw from the origin up to that point, a line, right? Very similarly, if I have a point over here, if I wanted to represent it as a vector, think of it this way, from the origin to that particular point is the direction of the vector. Every vector has a magnitude, every vector has some kind of angle, right? So, of course, in PCA, the basis vectors, so again, the basis vectors will be orthogonal to each other. If one basis vector is like this, how will be the next vector which is orthogonal to it will look like? It will be completely 90 degrees to it, right? So when it computes the eigenvector for the corresponding to the highest eigenvalue, it basically takes a look at which way is the data distributed the most. Okay, so if you take a look over here, the orientation of the data is this way, right? So the eigenvector corresponding to the highest eigenvalue will be in this direction. Okay, and then obviously the next vector corresponding to the second highest eigenvalue will be orthogonal to each other in this direction. And very similarly, if there were 3 dimensions, third one will be orthogonal to all of them and so on, right? Okay, so now let's take a look at this eigenvector, which is in the direction of the data where the data has the highest variance. So the important thing to remember is that vector, or the eigenvector, corresponding to highest eigenvalue is in the direction where data has the highest variance. And very similarly, the next one is in the next direction where there's the highest variance and so on, right? Okay, so if now we project any data point. So if we project this one onto this eigenvector, this to this eigenvector, right? For example, try to see the difference between these two data points. Okay, if we were using the standard x-axis as the basis vector, and if we projected these 2 points on the x-axis, is there any difference between the two data points?
Not really that close.
No, right? So if I magnify it like this, okay, if I project it over here, the contribution of this in the x direction is this much, right? If I project it over here, the contribution of this is very similar to this one. So you cannot distinguish between the two. Let's pretend this is digit 2, this is digit 5. The classification will be very difficult because if we are using the standard x, but on the other hand, if the data is more oriented this way, then you can see the projection of this will be here. Projection of this like go 90 degrees here. Is there a big difference between the two now?
Yep.
Yep. So that's the fundamental idea behind the PCA, which leads to a better classification because it's separating the data one from another. So even if we had a group of 2s, group of 5s, the difference between those gets enhanced. Okay? And the nonlinear PCA further does the same thing, even better. Okay. So, the other concept to remember from here is that if our data is not centered around the origin, so if our data is somewhere here, right? If we don't do the mean adjustment, then the PCA does not do as good of a job of a classification, okay? Because then the shift from, the axis, either the x or the y or the z, becomes dominant in the classification process. So as we take the mean out of it, it's essentially eliminating the effect of the shift. To give you another example that you can easily recognize, let's say we were doing face recognition. Here's a picture of, let's say, some famous soccer player, Ronaldo, right? Okay, and our recognition system can easily recognize it, right? Okay, let's say we took another picture of Ronaldo, same Ronaldo picture, but it is shifted to the left or shifted to the right. If our recognition system was not taking into account, eliminating the shift, it will not recognize it. It may even recognize Ronaldo as somebody else, even though it is Ronaldo. So this way, from the camera where the Ronaldo appears, if we take out the mean out of it, helps it in that direction, right? Okay, so now let me introduce another important concept. Okay, so let's say we are creating a deep network. Here's some layer, regardless it's doing nonlinear PCA or something additional. As we go along, you'll see what are the other possibilities. But we have many, many layers. Okay, so what happens is as we pass the data, so there's some data X, right? Input data X, doesn't matter what dimension it is. If you take a look at each and every neuron, isn't there a bias involved?
Mm-hmm.
What does the bias do? It simply shifts the data up or down, right? Plus will move it up, right? Okay, so what happens is, especially in the beginning, when we have initializes the biases randomly, okay, whatever output it's producing can shift, so can have a greater shift over here. Okay, similarly, that shift may get magnified over here in the next layer and so on. So So some time ago, some researchers came up with the idea, as we go from one layer to another layer, exactly like the PCA, let's do subtract from mean of all of this. And also, I forgot to tell you this, and this is true in PCA as well. We actually do two things. Okay? One is we mean adjust the data, which is easy, as you guys saw, compute the mean of every column, subtract it from each, right? We also do a variance adjust. So in a variance, so the typical procedure is like this. If you have some data X, then mean adjustment, as we talked about, will be minus the mu vector, right? The variance adjust will be take the square root of this and divide by this. Okay, so this way what happens is, the net effect is, if variance is too small, meaning the data is very, very close to each other, and if this quantity is less than 1, what will happen?
Spread it out.
It will make it bigger. It will spread it out. On the other hand, what if the data is too far out? Then this will bring the data closer. Okay. So the question is, in case of this X over here, what mean are we talking about? If you have a single data, does it have a mean? No. But as you recall, whenever we train a neural network, what algorithm do we use?
Mini batch.
Mini batch, exactly. So if we focus on the mini batch, suppose there are 32 inputs in each mini batch, will it have a mean? Will it have a variance? So that's exactly, if we, in every layer, if we kept subtracting the mean, dividing it by the variance, what will it do is it will hold the data during training closer, not too close, not too far. Okay, so this is what we call the covariate shift. So we'll control the covariate shift over here, here. If we adjusted every data like this, okay? So anyway, some people came up with an algorithm to essentially do this over the mini batch, and then they experimentally showed that this gives us a much faster learning. I mean, you can use a faster learning rate. So remember, in a learning rate, in the gradient descent, it was theta minus lambda delta of theta, some loss function over here, right? Okay, this lambda was our learning rate. Okay, if we did not use this shifting of the mean shifting of the data, covariance shifting of the data, then typically to get good accuracy, we will need to have a low learning rate. For example, 0.001. Okay, but if after every mini batch pass, we were adjusting this according to this rule over here, then we can increase the lambda to maybe 0.1, and it will do a great job. Okay, so as a result, what's the disadvantage if the lambda is too low?
Takes time to convert to the ultimate minimum.
It will take more time. You have to go through thousands of epochs to, get it to converge to a final value. Lambda 0.1, as you can easily see in this example, is 100 times better, 100 times faster. So the technique that I will show you is called batch normalization. And after going through PCA, now you can easily understand the motivation for it. Again, fundamentally, the idea is very simple. As you are training, whatever outputs are being produced, align them to the center by subtracting the mean. Also scale them according to the variance so that the data does not go too far or too close to each other, right? So next thing I will do is show you the actual math. How do we program it? I'll give you the code. You will program it by looking at my code and understand it 100%. Okay, go ahead.
What is the ultimate goal of bias? So my question is, can we eliminate bias in any one of the layer while doing the what do you call the last?
Yeah, bias essentially is shifting it up or down. In some cases, it is needed. For
Autoencoders, can we just eliminate bias and study the effect of bias in the encoding? And does it have a really good effect on the manipulating?
I haven't tried eliminating it, but I assume if it was the case, somebody would have already pointed that out. You guys can easily eliminate it and see it because the code will be given to you. But my feeling is it does. See, again, to explain the meaning of the bias, right? Suppose I have a data which is linearly separable. And the equation of this line is y equal to 0.3x plus 2. Okay, if we were using a single neuron, and if we did not have a bias of 2, there's no way we'll be able to learn that boundary. So the bias is needed, otherwise even simple things like this will not work. Okay, so to save time, I'll give you all the derivation of the batch normalization. Quickly point out how it's implemented. We'll come to the final, just like softmax, our final derivation was a very simple equation. Very similarly over here, you'll see it's a very simple answer at the end, but the derivation is a little bit tedious, not too difficult. This is not good news. Okay, let me try direct HDMI. Give me 1 second.